Find the moment of inertia about the axis passing through the 0 centimeter mark and compare the result with the result in part A. Now we need to find the moment of inertia of these two objects about an axis that passes through the center of mass using the parallel axis theorem. Now, according to the parallel axis theorem, I0, well, I0 stands for the moment of inertia of these two objects about an axis through the 0 centimeter mark. I0 equal to I center of mass plus mh squared, where h is the distance of this axis from the axis that passes through the center of mass. And tell me, what is that distance here? What is the distance between an axis that passes through the 0 centimeter mark and the axis that passes through the center of mass? That h equal to 0.6. And what does this m stand for? M is the total mass of the system, which is 2 kilogram plus 4 kilogram, that is 6 kilogram, isn't it? So the total mass of the system is 6 kilogram, and the distance of the axis that passes through the 0 centimeter from the axis that passes through the center of mass is 0.6. So m is 6 kilogram, h is 0.6, and therefore we have I0 equal to I center of mass. We just calculated the moment of inertia of these two masses about an axis that passes through the center of mass, and we got that as 0.27 kilogram meter squared. So I0 equal to 0.27 kilogram meter squared plus 6 kilogram times 0.6 meter squared, that is 2.43 kilogram meter squared. Do you remember this value? This is exactly the same result we obtained in part A. Is that right? So, using parallel axis theorem, we get the same result we calculated in part A. We calculated in part A the moment of inertia about an axis that passes through the 0 mark as m1 r1 squared plus m2 r2 squared, and we got the same result. Okay, another problem. Two masses are suspended from a pulley as shown on the right. The pulley has a mass of 0.2 kilogram and a radius of 0.15 meter and a constant torque 0.35 Newton due to friction between the rotating pulley and the axle. So there is a constant frictional torque. 0.35 meter Newton is the frictional torque between the pulley and the axis of rotation. Means that will be opposing the rotation caused by an external torque. Well, if m1 equal to 0.4 kilogram and m2 equal to 0.8 kilogram, what is the magnitude of their acceleration? If you remember, we talked about the motion of connected masses earlier on, about 2 or 3 lessons ago. Now, we will use the same concept here. The only difference here is that now the friction between the pulley and the axis of rotation is taken into consideration. Earlier, we did not consider that. So, what we're going to do is, we are going to isolate each object. We will look at the net force acting on M1. We will look at the net forces acting on M2 and use the law of motion, F net equal to ma for m1 and m2, because the motion of m1 and m2 are both linear. So we can use F net equal to ma for these. But when it comes to the pulley has a rotational motion. Now, what is the net torque on the pulley? There will be a torque, an external torque, and then there is a frictional torque. The net torque will be the external torque minus the frictional torque. And what is net torque equal to? The net torque equal to I alpha. So we are going to produce three equations. One equation for the motion of the mass m1, a second equation for the motion of mass m2, and a third equation for the rotational motion of the pulley. Alright, let's do that. Since the pulley offers friction, the tension on the string on the right and on the left will not be the same. You see, in a previous case when we did a problem like this, we said the tensions on each part of the string is the same because they represent the same string, and the pulley at that time was frictionless. Since there is friction between this pulley and its axis of rotation, the tension on the string on the right is not the same as the tension of the string on the left. So let T1 be the tension of the string on the right. So this is T1. The tension on the string on the right is T1. And let T2 be the tension on the string on the right. Okay. Now, in which direction you think the system will be moving? Let's identify the forces acting on M1. Since M2 is a bigger mass, we would assume that the system is going to move like this. M1 is going to move up and M2 is going to move down. So, let's identify the forces acting on M1. Tell me, what are the forces acting on M1? Of course, the weight of M1 will be acting vertically down, and the tension T1 is acting vertically up. Let's first of all find the weight. The weight of M1 is M1G. Its mass is 0.4 kilogram. Multiply that with G, you get 3.92 Newton, and that is acting vertically down. 3.92 Newton is acting vertically down on M1, and T1 is acting vertically up. So the tension T1 acts vertically up. Assuming that M1 moves up, that's what we had started with. Because M2 is greater, we would assume that M2 will move down and M1 will move up. We have the net force on M1 is T1 minus 3.92. Now remember, we are only considering the magnitudes here. So T1 minus 3.92 is the net force on